Hey everyone, my name is Alon Graber, and this is a tutorial for how to use the NumPy Python library. Now, I think it's more fun to learn Python libraries through examples. So we're going to go through an example of analyzing and predicting stock prices for the S&P 500 index. We're going to walk through how to do this with linear and polynomial regression. Now, you don't need to remember everything about linear and polynomial regression in order to do this. I'm going to walk you through everything. But this tutorial is going to assume that you already know how to use the basics of Python and that you have a computer with Python installed and ready to go. I'm also going to assume that you've downloaded the CSV file that's included in the description. It's called SPX Historical Prices. And we're going to use that in the tutorial. So go ahead and download that and then put it somewhere on your computer where you're going to run Python. I recommend for this tutorial that you follow along and type in the commands to get practice with them. If you get stuck, I've also included in the description a link to the code so that you can look at the code and figure out what went wrong. So without further ado, let's go ahead and get started by importing the libraries that we're going to need. The first library that we're going to need is going to be NumPy. So in order to import NumPy, we're just going to do import NumPy, and by convention, we're going to rename that to NP. So we're also going to need a library called pandas. So I'll talk a little bit later about what pandas does, but for now we're going to import it, and that's traditionally abbreviated to PD. And the last thing that we're going to need is a library called matplotlib, and that's going to help us with the plots that we're going to draw later. So we're going to just import that. And once we have those imported, we can go ahead and start loading in our data. So pandas is a library that works with these things called data frames. You can think of a data frame kind of like a spreadsheet that's built in to the library. So what we're going to do here is create a data frame for our data. So I've called this variable pricesdf for a data frame, and we're going to load it using the pandas read CSV function. And then here we're just going to give it the name of the CSV file. So once we have that loaded, we can take a quick look at what's in it. And as you can see here, we have one row for each date. So this is going back to 1978, and we have about 11,000 rows, one for each day, going to March 31st of 2023. We also have several columns here, so one for the open price, one for the high price, one for the low, and one for the close. We are just going to use the open price, and we're going to use that as our dependent variable in this analysis. So in order to do that, let's go ahead and just pull out this column. So we can do that by doing pricesdf and then using our square brackets and using the column open. And there's this special function that pandas nicely provides to us called toNumPy, and that's going to turn our column into a NumPy array. So once we've done that, let's go ahead and take a look at what we have here. So if we just print this out, we can see that NumPy doesn't print the whole thing, but it tells us that this is an array. These are some of the values in it. We can also print out what's called the shape of a NumPy array. And the shape is basically the dimension, all of the dimensions. So in this case, since there's only one number here, this is telling us that it's a one-dimensional array. Whereas if we saw like a number and then comma another number, that would be a 2D array. NumPy supports any number of dimensions. So we could have an array with 5 or 6 dimensions. In our case, we're going to basically be sticking to 1 and 2 dimensional arrays. The next thing that we need to do is create an independent variable. So the independent variable in our case, we could use the date that is listed here, but it's going to be easier if we just use a count. So this is just, we're going to create a new NumPy array that's going to be the count of the data, or the count of the column. So that's going to run from 0 up to 11,408. Now there's a special NumPy function for this called arange. So it works very similar to the Python range function if you've used that before. And that's going to just be where you give it a start value and an end value. So in this case, the start value is going to be 0, and then the end value is going to be this number, 11,409. And we're going to do that using the shape parameter, and then the bracket 0 just gets the first number out of this list of numbers, which in this case is going to be 11,409. So if we print out x now, we can see that this is just a simple array of counts. The last thing that we need to do before we kind of get started is we're going to reshape this. So right now, this is also a one-dimensional array, but in the future, we're actually going to need this to be a two-dimensional array with a length 1 here, which is similar but not the exact same in the world of NumPy. So what we're going to do is we're going to use the reshape function. So the reshape function takes two parameters. One of them is the axis, so that's in which direction we want to add a new dimension. So in this case, it's going to be -1 because we want to add it to the end of this list. And then we're going to add one dimension to this, or a dimension of length 1. So now if we check the shape, we can see that now we've added a second dimension of 1. And it looks similar, but we can see that if we print out the variable that it does indeed look two-dimensional. It's just that we don't have anything in this other dimension. Now to finish up this first section, what we're going to do is we're just going to plot this. So we can use the plt.plot function that we imported earlier, and we're just going to give it the two variables that we want to use, the x and the y values. And in order to actually show this, we're going to use the show function. We can see that this pulls up a plot where on the x-axis we have our index, so that's the variable that we created that goes from 0 up to 11,000. And then on the y-axis we have the actual value of the S&P price. So what we're going to do in the next section is we're going to start by fitting a linear regression line. Now that we have our data loaded, we're going to start with the process of fitting a linear model. As a reminder, a linear model fits the form y = ax + b. We're not going to go through the formulas for calculating what a and b are, but what we can do is we can use another Python package to calculate those for us, and then we can use those a and b values to make some predictions and then plot those predictions. So in order to do this, we're going to use a function from the scikit-learn package. If you don't have this installed, it's pretty easy to install. You can Google how to do it, but if you do have it set up and ready, you can use this to import. So from the linear model subpackage, we're going to import this function called linear regression. So from here, what we're going to do is create a model. So the model is going to be using this linear regression function, and then we're going to use the .fit function. And what this is going to do is this is going to compute our a and b values. So once we have this done, we can use the model and pull out the a and b values. So the a value is going to be called coefficient. So we do model.coefficient, and it has an underscore at the end. Make sure not to miss that. And then the b value is going to be the model.intercept. And we can see that if we print out our a value, we can see that this is a one-element array, and that element is going to be the A value. And then for B is not an array, it's just a single value, and that's going to be our y-intercept for the equation. Now, the next thing we're going to do is we're going to actually make the prediction. So we're going to create a new variable called y-prediction. And normally you might be thinking that we would do something like A times x plus B. So the problem with this is that A and X are arrays. And in NumPy, when you do the multiplier sign with two arrays, what it's going to do is it's just going to multiply each element by each element in the other array, which is not exactly what we want. What we want here is we want a dot product. So what we do is we do x, and then the @ symbol is what NumPy uses to indicate that we want a dot product. So we can do x at A plus B. And in this case, the plus B is going to add that to every element in this array, and it's going to create a new array for us. So what we can do is we can check that the shape of this output array is what we want. So we can see that we have some values that look possibly correct. And we can check that this is going to be the same shape as our y values. So just like our y values, this has the shape of, it's a one-dimensional array with a length of 11,409 in that dimension. So now that we have these values, we're going to go ahead and make a new plot. And we're going to include the x and y values as before, but we're also going to include our predictions. And this is going to create the plot, and then we can use the plt.show command to actually show the values. So once that finishes, what we're going to see here is we're going to see our original series in blue, and then we have our predicted values using the linear regression in orange. So there's one value for each index here, and we can see that we have our linear model here, the line that's going through here. So we can see that this is not a terrible prediction, but not super great. We have kind of some areas where it's not under predicting and some areas where it's over predicting here, and it doesn't seem to do very well kind of near the end of this graph. So now that we have this done, we're going to move into the next section and see if we can improve on this prediction. We're going to look at polynomial regression as a possible alternative to using to get some more accurate data. So now that we finished linear regression, we're going to go through and try polynomial regression to see if we can get a more accurate fit for the data that we're looking at. So in order to do that, we're going to take a quick look at what polynomial regression looks like. So many of you might be familiar with polynomial regression in the form of ax squared plus bx plus c. And this works, and we could use this, but it's going to be a little bit easier if we rewrite this slightly. So this is going to be in the form of a dot, and then we're going to have an array here of x squared and x plus c. And you can take a moment and convince yourself that this is indeed the same thing. So based on the way that the dot product is defined, this is going to expand out during the calculation, and we're going to get a0 times x squared plus a1 times x plus c, which is the same thing. But the advantage is that if we use this form, we can compute all of our coefficients at the same time, and we can use the NumPy dot operator to handle all of this multiplication at once. So now that we have an understanding of what we're going to do, let's go ahead and jump into the implementation. So what we're going to do is first we're going to make this array that includes x squared and x. So the way that we're going to do that is we're going to create a new variable called xpoly. That's short for polynomial. And we're going to use the NumPy hstack function. So hstack creates a horizontal stack of everything that you provide in this list. So in our case, what we're going to do is we're going to provide x as the first variable, and then we're going to provide x squared as the second variable. So what NumPy is going to do here is it's going to create a new array that has the same shape, and for each element in it, it's going to square it, and then it's going to create a new two-dimensional array of both of these and horizontally stack them together. So when we run this and we print out the output, we can see that we have this nice two-dimensional array, and we can verify that it's two-dimensional by printing out the shape. So we have 11,409 in the first dimension and then 2 in the second dimension. So here we have this column which contains the original values, the original x values, and then in the second column it contains the x squared values. So from here, what we need to do is calculate those two a coefficients. And the nice thing about the linear regression that we used earlier is we can use the exact same linear regression functionality to compute both a coefficients at once. So we're going to still use the linear regression function that we used earlier, and we're going to fit it to xpoly and y. So what this is going to do is this model, instead of having a be just an array of length 1 as it was before, the coefficient that comes out of this model is going to have two values. So these are going to be our a0 and a1 values. And the intercept is going to work the same. We're going to call it b. So we're just going to do model.intercept. And this is going to be a different value than we had before because it is fitting differently. It is worth mentioning that this works pretty well with 2 dimensions, or with an x squared function, but there is actually an alternative way to do this using scikit-learn. There's another function that you can use. So I'm just going to demonstrate this here. You don't need to follow along with this step, but it's good that you know that this is here. So scikit-learn includes this function called polynomial features. And what this is going to do is we can create this xpoly using the polynomial features function. And we do degree equals 2 so that this knows that we want to generate x and x squared. We don't want to include the what's called the bias term, which is going to be our b value. We don't want to include that here. And then we're going to run it with this function called fit transform, and then that's going to be our x value. So now we can confirm that the xpoly that it creates here, the values look a little bit different, but these really are the exact same values as we had before. They're just written in scientific notation this time. But we can see that the values at the start and end are definitely the same values. So this could be used differently. And the cool part is that if you wanted to use this, you could change this degree and you could get cubic or quartic functions if you wanted to change how you're modeling. So now that we have all of this done, I'm just going to go ahead and change this back so that the values look the same. And we're going to go ahead and create our prediction values. So we are going to use the y prediction function, and we're going to take our polynomial values and we're going to do the dot product with the coefficients. So notice that this is the exact same function that we were using before. And this is really a testament to the power of NumPy, where this is going to work this function itself for computing the predicted values is going to work regardless of how many dimensions are in our coefficients and regardless of how many dimensions are in our poly features. And that's going to enable you to experiment around with different degrees of polynomials and different features very quickly and easily. And NumPy is going to handle all of the dimensions and computation for you. So once we have those prediction values, maybe we should verify that this is in fact the right shape. So we did get the shape that we expected, which is the same shape as before. And now all that's left to do is to plot them and see how they look. So again, we're going to do x, y, and y predicted. And then, as usual, we're going to use the plt.show function. And once we get that showing up, we can see that we have our polynomial fit. So in this case, we have a parabola that's kind of facing upwards, and we can see that this does seem to fit our data more closely. Although this is probably not the absolute best way to model stock market data. As you can see, this is kind of going upwards back here, which is not a great sign because we would probably assume that the data doesn't actually extend looking like that. But it does seem that in this range, it does fit our data a lot better than the other line did. So I hope you enjoyed walking through this tutorial. I think that this is a very interesting way to learn NumPy, and I hope that this shows you kind of the power of the library and the power of the Python scientific computing stack. And if you want, I'm going to link more tutorials and in the description below so that you can continue learning more about how this works. Thank you.